Good morning, everybody. Hope you are all healthy and safe at home. So let us continue with our section 18.1 on contour integrals of our fourth module. So in this lecture, we are going to discuss about the theorem, a theorem which will help us to find the bound of the contour integral. So in the previous lecture, we had discussed how to determine the contour integral, and we had seen few examples related to it. In this lecture, what we'll do is we will find a bound for that contour integral. So let's move on to the theorem. It's called the bounding theorem, or sometimes it is called as the ML inequality. Okay, so let's see. If f is continuous on a smooth curve C, and if modulus of f of z is less than or equal to capital M for every z on the contour C, then modulus integral over C f of z dz will be less than or equal to ml, where L is the length of the curve. Okay, that is, we are given a function f on a smooth curve C, and if the modulus of f of z is less than or equal to m, that is, the mod f of z is bounded, then integral over C f of z dz would be less than or equal to m into L, where L is the length of the curve. Okay, so we have two terms, that is m and L. Okay, and function f of z will be given to us if you are asked to find the bound. So m is actually the bound of f of z, and L is the length of the curve. So these are the two things that we'll have to determine the bound of the contour integral. So let's just move on to the theorem, and a small proof which is pretty much simple is given in your textbook. That is, we know summation of k equal to 1 to n f of zk into delta zk. This is how we will get the terms in case of partitioning the curve. This is clearly less than or equal to summation mod f of zk into delta zk, right? Modulus of a plus b, or that is the triangle inequality, that is mod of a plus b is less than or equal to mod a plus mod b, or mod z1 plus z2 is less than or equal to mod z1 plus mod z2. Now f of z is always less than m, right? So I can write this as less than or equal to m into delta and m into summation k equal to 1 to n mod z of k star, z of k, right? Because every f of z is less than or equal to m by the theorem. So this is less than or equal to m into summation k equal to 1 to n and into modulus delta zk. Now what is delta zk or delta xk and all? It was the difference between xk minus 1. That is the length of that small portion, right? Okay, so it is actually the length of a small chord joining the points zk and zk minus 1. So taking the sum of all these, that will never be greater than the length of the curve, right? Because we are partitioning the given curve into small chords, so that that summation of the length of each portion, okay, if you take the sum, that can never be greater than the length. So this value will always be less than the length of the curve, that is capital L. Okay, so we get summation k equal to 1 to n f of zk into delta zk is always less than or equal to m into L, where L is the length. So as now p tends to 0, we can say that integral over c f of z dz is less than or equal to ml. So it's pretty much simple proof. That a bound will always be m into L. So let's just see an example related to that. Now we are asked to find an upper bound for the absolute value of integral over c e raised to z by z plus 1 into dz, where c is a circle, mod z is equal to 4. Okay, so we are given the function f of z, and we are given the curve c is a circle, mod z is equal to 4. Okay, so what all do we need? We need to find the bound of f of z, right? That is modulus of f of z. What will be modulus of f of z? So here f of z is e raised to z by z plus 1. So modulus of e raised to z by mod divided by z plus 1. What is that value we have to determine? Now for this, this can be written as modulus of e raised to z divided by modulus of z plus 1. Okay. Now modulus of z plus 1 is greater than equal to mod z minus 1. Okay, that is mod z plus 1 is greater than equal to mod z minus 1. We have done this in the section 17.1. You can refer to it. Okay, so mod z plus 1 is greater than equal to mod z minus 1. So when we take the reciprocal, the inequality sign will be changed, right? So 1 by mod z plus 1 would be less than or equal to 1 divided by mod z minus 1. I hope that concept is clear with you people. If we have mod z plus 1 is greater than or equal to mod z minus 1, okay, then 1 divided by mod of z plus 1 would be less than or equal to 1 divided by mod of z minus 1. Okay. So this inequality becomes this is less than or equal to mod of e raised to z divided by mod z minus 1. Now we can determine the value of all these. So modulus z is given to be 4. So what will be 4 minus 1? That is 3. So the denominator value is 3. Now modulus of e raised to z, because we don't need the bound in terms of any complex number or any variable. We need to be a perfect value. Okay. So modulus of e raised to z, how can we determine that? What will be modulus of e raised to z? It will be nothing but e raised to z can be written as e raised to x into e raised to iy, right? We have done this before. E raised to z is e raised to x into e raised to iy. And what will be e raised to iy? That will be cos y plus I sin y. So this will be mod e raised to z is nothing but modulus e raised to x into cos y plus I sin y. Now what will be modulus of cos y plus I sin y? Cos square y plus I sin root of cos square x, cos square y here, cos square y plus sin square y. So that is nothing but 1. So this is nothing but e raised to x. Okay, so this modulus I can write it as this is less than or equal to e raised to x by 3. Now one more thing, we are considering the circle mod z is equal to 4. So that is the circle with center 0 and radius 4. So the value of x can never be greater than 4, right? It will be bounded between that portion but with the radius of the circle. So x is always 4. So this is less than or equal to e raised to 4 by 3. So we have got the modulus of f of z is less than or equal to e raised to 4 by 3. That is, we have computed our m. Okay. Now we need to find the length of the curve. Now what is the length of the circle? It is nothing but the perimeter of the circle. Of radius, here it is 4. So what will be our perimeter? Perimeter is 2 pi r. That is 2 pi into radius is 4. 2 pi into 4, that is 8 pi. So the bound is nothing but 8 pi e raised to 4 by 3, right? So this is how we determine the bound. So we shall do more examples which will help us to determine the bound easily. That is, we have to do a bit calculations here and there to determine our m and l. Here l is usually simple, that is the length of the curve. Then to determine the bound of you'll have to work on it. So that is what our bounding theorem stated. That is, if modulus of f of z is less than m and if the length is known, then we can determine the modulus of the integral of that function. Okay. So now let's move on to just two definitions. With that we'll end up this section, that is of circulation and net flux. We are familiar with these terms in the previous sections and all. So here to determine, if you are asked to determine the circulation and the net flux, we just have to calculate one integral in case of complex case, that is integral over c f of z bar into dz. Okay, now we know how to determine integral over c f of z dz. So we just have to determine integral over c f of z dz, f of z bar dz. So that will be a complex number. So the real part of that complex number is called the circulation and the imaginary part is called the flux, net flux. Okay, so just remember this formula, that is circulation is the real part of integral of f of z bar into dz, and the imaginary part of integral over c f of z bar into dz gives us the net flux. Okay, so let's just see an example which is given in your textbook. That is, we are given the flow f of z is equal to 1 plus I into z. Okay, and we are asked to compute the circulation and net flux around the circle mod z is equal to 1. Okay, that is, first we will evaluate integral over c f of z bar into dz. So here we are given the circle mod z is equal to 1. So it will be easy if we consider z is equal to e raised to it, right? So we have z is equal to e raised to it, and so z dash will be equal to I into e raised to it. And what is the variation? Circle of length 1, so radius 1, so it will be t varies from 0 to 2 pi. Okay, and now we need to know what is f of z bar. F of z is given to us as 1 plus I into z, so f of z bar is nothing but 1 plus I into z bar. Okay, so if z is e raised to it, what will be z bar? Z bar will be nothing but e raised to minus it. So we can easily evaluate. So integral over c f of z bar into dz is nothing but integral 0 to 2 pi. F of z bar is 1 plus I into e raised to minus it into dz is z dash of t, that is I into e raised to it into dt. So e raised to it gets cancelled, so it will become we can take e raised to I, so it will be 1 minus I into integral 0 to 2 pi into I into dt. Now when we multiply it by I, we will get 1 plus I, that is 1 minus I into I is nothing but I plus 1, that is 1 plus I. So we get 1 plus I into integral 0 to 2 pi into dt. So that is nothing but 2 pi I into 1 plus I. So that is 2 pi plus I into 2 pi. So the real part of this integral is 2 pi and the imaginary part is also 2 pi. That is a coincidence in this case. So the circulation is 2 pi and the net flux is also 2 pi. Okay, so the facility in finding the circulation and net flux in case of complex variables is that you just have to determine one integral, that is integral over c f of z bar into dz, and that integral will be a complex number. So the real part of that complex number gives us a circulation and the imaginary part gives us the net flux. So in this lecture we had discussed about the bounding theorem to find the bound of the contour integral and finding the circulation and net flux. So that's it. With this we shall wind up today's session. Thank you. Stay home and stay safe.